So the last time we wanted to look on some stuff with vectors. And before we start, there are a few things that we need to know about vectors, okay? Kind of like to break the CSEC topic vectors into 4 parts, you know. What is a vector? The different types of vectors, what position vectors are, and then how we can use them with vector geometry. So in the chat for me, on a scale of 1 to, all right, let me say on a scale of 0 to 10, write down how comfortable you feel with vectors. Where would you put yourself? Are you at a 10? Are you at a 15? Are you at a -3? Where are you? All right. All right, my same is there. So, all right, no problem. So we're going to add on to those. We're going to make sure that those turn into at least 8s and 9s and 10s. Right? Because let's kind of first start by focusing. Oh, looking in the chat on YouTube as well. Seeing some 4s and 5s. And some 3s. Okay. All right, no problem. So the reason why I ask that is because you basically can split vectors into these 4 parts. So you see, once you get the idea for what a vector really is, it all starts from there. Okay. So let's write down the definition of a vector. A vector is something that has, oops, oh, that kind of looks weird. A vector is something that has magnitude and direction. Okay. So it has magnitude and direction. And you know, oftentimes vectors they look like that. Okay. So anything that has a size and it can tell you where it's moving to, that is what we call a vector. So for example, something like velocity is a vector because it has a speed, like it tells you that it's moving at 80 kilometers per hour, and then it will tell you where. It will tell you like east or west or so on. So that would represent a vector. Okay. Something else that would be a vector is force, because you can apply a force in a certain direction. If you and somebody fighting and you thumb this way, it's different than doing it this way. That makes sense. So once it has a direction and a size, then it's a vector. Let me ask you guys a question just to see if you get the idea. Would you say that let me write it right here. Would you say that mass is a vector? So would you say that mass is a vector? Put a Y in the chat for yes, and put a N in the chat for no. So remember, a vector has to have magnitude and direction. Would you say that mass is a vector? Let me see what you guys are thinking. What would you say? All right. All right, good. Yeah. Ramai saying no, persons in chat online are saying no as well. And that's right. Mass is not a vector because it has size, but it doesn't have a direction. Okay. Now you see, everything else that you're going to learn about vectors comes from this main idea. Because when we go into types of vectors, there are 3 types of vectors that you can define them based on the definition of a vector. We have equal vectors that have the same size and the same direction. Right? We have parallel vectors that have just the same direction. Okay. And then we have opposite vectors. Okay. Because opposite vectors, now this one messes up students sometimes, but it has the same size. It has to have the same size, but opposite direction. So it's completely opposite of the other one. Okay. So those are the three ways that we can describe the three main different types of vectors. Right? Have you guys ever seen those definitions before? Are those different types? Have you ever heard about them? Have you ever seen them? Because we can split them up, as we say, into those three different types, right? So if you haven't, then it's something to keep in mind, because as we say, it all comes from there. That's anything that we're going to do with vectors, we have to know those three things. Now, when we talk about a vector, it can be written in this form. So just covering some ideas. It can be written like that, okay, where the movement in the x direction is at the top and the movement in the y direction is at the bottom, okay? So whenever we're dealing with a vector, we can write it like this. And probably you guys would have seen that before. So for example, if I have a vector that was 3, 4, what this is telling me, it's moving 3 units to the right, okay, because to the right is positive, to the left is negative, and it's moving 4 units up, because again, positive is up, negative is down, okay? So that's how we write vectors. That's how we can represent vectors. If I were to tell you that I had a vector that was, let's say that it was -2 and 4, what does this vector mean? What does it mean? Write it in the chat for me. What does it mean? -2, 4. What that vector really mean? Where am I going? Because remember now, vector just represent movement. So what that means? Let me see what you guys are thinking. What that mean? Right. I'm seeing Alyssa is thinking 2 units left, 4 units up. Yeah, and that's right. Good job, Alyssa. Yeah, that's it. So 2 units to the left, because you're going, remember, up at the top is negative is to the left, and 4 units up, because down here it tells you whether you're going up or down. Yeah. Personally, I use left hand, so I think they should have made negative be right, but yes. So them going still. So 2 units to the left and 4 units up. That's what that would mean. So that's how we can interpret our vectors. Now, when we talk about position vectors, those are vectors that start at the origin. Okay. Those are vectors that start at the origin. So anyhow you have a vector like this. Let me put it here and here. Once you have a vector that starts from the origin and goes outward, something like this. Let me draw that properly. That would be a position vector. And we know that a position vector, if this was a point P, then the position vector would be OP. And then finally, we focus on vector geometry. And vector geometry basically uses vectors on geometric figures. So that's in the exam where you might see them have a vector on a parallelogram or on a triangle, and you're supposed to figure out how different types of vectors link back or can describe what's happening on that geometric figure. All right? So those are some of the main things that we need to know. So I want you guys just to make sure that and we're going to go through them. We're going to make sure that you get them as we go along. But just remember this, and I always tell students, just focus on these things. So these things right here, they are super important. The types of vectors, because that's where everything else starts, and the definition of vectors. So sometimes students feel that vectors are a very difficult topic, but if you just focus on the concept and not trying to remember a ton load of things, then it makes it much easier to do, right? And that's what we're gonna do right now. So let's jump into it. Let's jump into our first CSEC question. So here, this one says that the diagram below shows two position vectors OR and OS, such that R is the point 62 and S is the point -43. Write as a column vector in the form XY, vector OR, vector OS, vector SR. Find the magnitude of OR, and given that OT is 2,5, prove that OSTR is a parallelogram. So let's get started. First, we want to write as a column vector OR. So where is OR? Let me mark it on the diagram. Starts at O. Oops. It starts at O and it goes to R. Okay. And I already have it here marked out for us. So where does it stop? It stops at R, which is 6,2. So if that's the case, that means let me zoom in a little. That means the vector OR, it goes 6 units to the right. So that's 6 and 2 units up. So that would be the vector OR. All right. So remember, once we know the point, then that can basically tell us what the position vector is going to be, and OR is a position vector. Likewise, for vector OS, starts at O, put that in blue, and it goes to S, so it goes right here. So what would that vector be? What would the vector OS be? Write it in the chat. Let me see what you guys are thinking. What would the vector OS be? So remember, look at where it goes, where it starts and where it ends up. What would the vector OS be? Right, very good. Thanks for that, Simone. Good, yeah. -4, 3. So it would be, oops, let me write it properly. That is -4, 3. All right, good. Now, what about the vector SR? What does that mean? SR. It means it starts at S and then it goes to R. And the great thing about that is we have our diagram here to help us, because we can just draw that. So SR starts at S and goes to R. And now let's see if we can we can figure out what that vector is. What's happening here? Well, we realize it, let me write it like here. It goes down by 1, right? And then what happens? It goes across by how much? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. So it goes down by 1 and to the right by 10. So down by 1, we know that's -1, and to the right by 10. So that's +10. So that means vector SR is going to be equal to 10 in the X direction and -1 in the Y direction. So that's vector SR. All right. Anybody have any questions about that one, or is that one clear too? Why SR is 10 minus 1. right. That sounds like everything good. Sound like everything good. So guess what? Let's go and find the magnitude of vector OR. So what does that mean? Red magnitude. Whenever we're finding the magnitude of a vector, we're basically finding how long the vector is. And we can find the magnitude of a vector. Put it right here. We can find the magnitude of a vector by squaring the x component and the y component and then finding the square root of their sum. So that's the square root of the x component squared plus the y component squared. So we already know the components of OR, that's 6 and 2. So it's going to be the square root of 6 squared and the square root of, the square root of 6 squared plus 2 squared. 6 squared is 36, 2 squared is 4. So that means it's going to be equal to the square root of 40. Okay. So the magnitude of OR is the square root of 40. And what's the square root of 40? What is that? Let's work that out. What is the square root of 40? All right. This is Simone 6.3. All right, let me check with you. Yeah, that's what I got to. And it didn't tell us how much to round it to here. So I'm just going to put it to, I think I'm going to leave it at 6.3 units. I'm just going to say approximately because we approximated. So that's approximately 6.3 units. All right, good. So that would be our magnitude of OR. Okay. I should probably put that down here. Yeah, just in case. I'm gonna need space. Right? No, it says that given that OT is 2,5, prove that OSTR is a parallelogram. What does that mean? First, it says OT is 2,5. So let's the vector 2,5. So let's put that on our graph. So I run out of colors. We'll go back to yellow. So 2,5 means 2 in the x direction, 2 to the right, and 1, 2, 3, 4, 5 units up. So T would be right here because the vector OT is 2,5. And next, it says that we want to prove that.
Excuse me, I didn't see what you did a while ago. Can you just do it again? You get it?
All right, it says OT is 2,5. Oh, let me use my mouse over here. OT is 2,5. So it means that we go 2 to the right, 1, 2, and then 5 up. 1, 2, 3, 1, 2, 3, 4, 5. Oh, it should be up here. Sorry. So that is where T would be, because remember OT goes from O to T. So that means T must be up here. You following me? You get what I'm saying so far? All right, good. And everybody else online, we're good so far on YouTube. Good so far. Give me a thumbs up if you're following so far with why we put T there. We say why T would be at that point. Give them a little time just to tell me. No, I'm sure. All right, let's look back on the question. So it says, given that OT is 2,5, right? So think about it. OT. What does that mean? It means it starts at O and then it goes to T. So that means I'm looking for a vector. Let me actually draw it. That goes from O and goes up to some point T and that is 2, 5. So it's going to go 2 units to the left. It's going to go 2 units to the left, 1, 2, and then 5 units up. 1, 2, 3, 4, 5. So literally my vector would look like this. Let me draw it with a line. My vector would literally look like this. And if it's OT, it means it goes from O to some point T, which must be right there. So that's why I said that the point T is 2, 5. You see what I'm saying? Good now, Kalia? All right. Yeah. Now let's again, it says we want to prove that OSTR is a parallelogram. So let us look at it. OSTR. Where is that? Oh, you get it now. Good. So OSTR starts at OSTR. So I'm going to connect those. Then let me connect them. Use white as a line. So that means here's where a little geometry comes in. How do we prove that something is a parallelogram? What are the properties of a parallelogram? How do we know when something is a parallelogram? Can I write that in the chat for me? How you know when something is a parallelogram? What are they? What do we know about it? What do we know about parallelograms? Well, one thing we know. Oh, sorry. Go ahead. What's that? Simone, that was you? Oh. Okay. One thing we know about parallelograms is that opposite sides are equal and parallel. So if we want to show that OSTR is a parallelogram, we're going to have to find some way to show that the opposite sides are parallel and equal. All right? So let's do that. That's how we're going to show that. So showing that OSTR is a parallelogram. First, let's take the opposite sides. ST, you realize this is one. ST and what else? OR. So let's work with those two. So what is the vector ST? What is ST? Let's zoom in on that. So ST, oops, I should probably, it's kind of hard to see. ST starts here and it goes up here. So let's look at what that vector is. It goes to the right 1, 2, 3, 4, 5, 6 units, and it goes up 1, 2 units. So the vector ST is equal to 6, 2. 6 to the right, 2 up. Hey, Ninja, good to see you. So ST is 6, 2. And what do we know about its opposite side, OR? We already showed that OR is 6, 2. So that means those sides are opposite. The opposite sides are equal and parallel. Okay. Now, what about the other two opposite sides, which would be OS and RT? We already know that OS is minus 4, 3. So let's look at RT now. So RT, let me look at this line that I have. So that's what I'm going to use to count it. 1, 2, 3, 4 units to the left. So that's minus 4. And then 1, 2, 3. 3 units up. So that's positive 3. So RT, so let me write that likewise. RT is the same thing as OS, which is negative 4, 3. So since the opposite sides are equal, then that means it is a OSTR is a parallelogram. Okay? So that's how we can show that. We just need to show that the opposite sides are equal for a parallelogram. Right? No. Anybody has any questions about this one? Is this one clear? Are we good to go? So you have to pay very careful attention in vector geometry. Some of the things that you can use to show how some stuff are related. Clear. All right, good. Let me ask you a question just to make sure we know how to prove these things if they ask it. How would you use vectors to show that a figure is a square? How would you use vectors to show that a figure is a square? What would you do? How could you prove that? In other words, what would all of the vectors have in common? Let me see if you guys are thinking. How would you prove that? How would you prove? I don't know, you're going to take a little time to think about it. How would you prove it? How do you use vectors to prove if something is a square? Think about the geometric properties of a square. Let me see what you guys. All right. I'm seeing in the chat here. Oh, if it's you know, so I don't remember if it's a June 2021. Probably. I don't remember where I got this one, but it is a CSEC question. Opposite sides would have the same position. Vector. That means they would all be starting at the same place. But that's not necessarily the case with a square. So think about that one a little more.
Does it have anything to do with the magnitude, sir?
What about the magnitude? You're onto something. What about the magnitude? So you're onto something, you know. What do you know about a square? What do you know about a square?
Like all 4 sides are equal.
Good. So in the world of vectors, what does that mean for the vectors? And I think I'm seeing it here as well in the chat, equal length. Yes. So if you are going to use vectors to show that something is a square, you'd have to show that all of the vectors, all of the sides of that square have vectors with an equal length. And you can show that, Simone, by showing that their magnitudes are the same. You understand? So you just think about the geometric properties when you're answering problems like these. That's what you have to keep in mind. All right. All right, good. Yeah. Now let's try another CSEC question. It says the position vectors of point A, B, and C relative to the origin O are OA, which is 2 minus 2, OB, which is 6, 1, and OC, which is 10, 4, respectively. Expressing the form XY, the vectors AB, AC, and show that AB and C are collinear. First, let's start with AB. Okay. No, we don't have a diagram here, but let's oops, let me zoom back in. Let's kind of visualize it. What is it saying here? AB, what does that mean? Well, if we think about vectors, remember vectors deal with movement. So if you have 2 points, A and B, on some type of grid, where can I put this now? Let's just say for argument's sake, the grid looks like this. To get from, let me put the grid here. To get from A to B, we could go to the origin and then go to B. So the origin is always like this midway point that we can use. You understand? So likewise, that's the same thing here. If we're talking about a vector AB, it means we could go to our midpoint. So we could go from A, let me put A here. We could go from A to our midpoint. So A to O. And then we could go from O to wherever B is. So call it, say, let's say that B would be right here, okay? So AB is equal to AO plus OB. That makes sense, everybody? That part, that makes sense? So again, the concept of vectors, you just have O as that midway point, that central point that we're moving to. So AB is equal to AO plus OB. Now, what is AO? We don't know AO, but we know OA. OA is 2 minus 2. AO is an opposite vector to OA, because it's going in the opposite direction, equal but opposite direction. So that means AO would have to be the what's that word I'm looking for? It's like you would negate OA. So instead of 2 minus 2, it would be minus 2, 2. So AO, let me put that down here. AO would be equal to minus 2, 2. Right? So since that's the case, and there are different ways that you can do this, this way kind of shows the idea behind it, but there's also another formula that sometimes people kind of use to remember it, which is fine too. So that's AO plus OB. So what's that going to be? That's going to be minus 2, 2 plus OB, which is 6, 1. Minus 2 plus 6, that is 4. 2 plus 1, that is 3. So the vector AB is equal to 4, 3. Right? Now, what about AC? What is AC going to be equal to? Again, you can think about the origin as a midway point. So it's like we're going to, first we go to O, AO, and then from O to C, right? Because we don't have AC directly, so we have to figure it out using the information that we have. So AC is AO plus OC. What's AO? We don't find that already, minus 2, 2, plus OC, which is 10, 4. And then when we work that out, minus 2 plus 10, that's 8. 2 plus 4 is 6. So AC would be 8, 6. All right? Everybody good with that one? Let me know in the chat. That one clear? Everything good with that? I am not so sure. Kind of feel like lost. It's like, I don't know. Oh, you get that. Oh, you guys stay. I think I got the marks right for this question. I don't know why one is 1 and one is 2. That one, no, I can't tell you. I don't know why one of the vectors is 2 and one is 1. Who knows? All right, good. So you guys saying you're good. All right, good. Now, let us go to the third part. It says, hence, determine whether A, B, and C are collinear, given the reasons for your answer. Now, what does that mean? Collinear. What in the world of vectors, what is that? Well, if something is you remember when you were doing gradient, I would say that the points are collinear. You mean that all of the points are on the same line? It's the same thing with vectors. So if something is collinear, that means we're taking the points A, B, and C. We want to somehow prove that A, B, and C are on the same line. Right, yeah, all of them are on a straight line. Good. So if we're going to do that, that means that A, B, and C are going to have to share some common point. Okay? So they are going to have to share some common point, and they're also going to have to be parallel to each other. So if you don't have that, make a note of that. Two vectors are collinear if they share a common point and are parallel to each other. So if we're going to show that A, B, and C are collinear, we need to show that AB is parallel to AC and that those two vectors share a common point. Well, we don't need to show that they share a common point because the two of them already have A in it. So since both start at A, they share A as a common point. That one is pretty straightforward. So now we just need to show that they are parallel. So let's look at AB and let's look at AC. Because if you visualize it, come back here, it's on a straight line. So you're showing that AB is parallel to, let me put AC in yellow. It's AB is parallel to AC some. That's what you want to show. All right? So could I say AB is the blue one? All right, and AC is the yellow one. So now, let's take AB, which is 4, 3. And let's take AC, which is 8, 6. How do we know when two vectors are parallel? Let me see if you guys are familiar with that one. How do you know when two vectors are parallel? That's a condition. Ooh. What makes two vectors parallel? What do you know about that? So you can either write it in the chat or say it out loud. Say what you guys got to say. Or we're not so sure what makes two vectors parallel, or we don't remember. Right. Yes. That's it. Ninja. They share a common multiple. Mikkel, the truth. What about the truth? I don't know what you're talking about. But yeah, that's right, Ninja. They share a common point. So that means they share a common multiple, sorry. So you want to show that one is a multiple of the other. But look at that. Notice that AC, that's Tamaya, yeah, that's the right way to put it. They are scalar multiples of each other. That is it. So AC is equal to 8, 6, but you could say that 8, 6 is 2 times 4, 3. 2 times 4 would give you 8. 2 times 3 would give you 6. Okay? So if that's the case, that means, what do we know? We already know that AB is 4, 3. So it's really 2 times a vector AB. So here we have shown that AC is a multiple of AB. Therefore, they are parallel. AC is parallel to AB. Thus, since we have shown that they are collinear, they share a common point, and they are parallel, we can write that down. All right. So that's how we know they are collinear. So, oh, you make a mistake. I didn't. That was a truth. What are you talking about? Everybody good with that one? Everybody sees that it is. Everybody has any? Not so sure. Or is like, okay, I see what you're saying. We'll see. Let me see in the chat what you guys saying. Good. All right. All right. Good, good, great. Good. Now let's move on. I think, yeah, this is our last question. Now we're gonna go into a little vector geometry. I remember I said if you're dealing with vector geometry, and on a video in my channel too, I had that, where it says once you're dealing with vector geometry, you always want to remember to know when to find out when vectors are equal, parallel, and opposite, because that is what you use to solve problems like these. So keep that in mind as we go along. Now, in this problem, it says, do I have the right thing here? Oh, yeah, no, yeah. In this problem, it says in the diagram below, not drawn to scale, shows a quadrilateral ABCD in which AB is equal to M, DC is equal to 3M, and AD is equal to N. Complete the statement below on the geometric properties of the following vectors. AB and DC are blank, and AB is whatever times CD. I think, you know, I think this should be DC. I think this should be DC, you know. I don't remember. I wonder if I wrote that right. Not sure. I'm just gonna leave it still. Just gonna leave it still though. So remember, we're looking out for which ones are those. So AB and DC. First, let's find AB. Where is AB? AB is right here. And what do we know about AB? AB is vector M. Okay. What do we know about DC? Well, it already told us at the top. DC is 3M. So one is a multiple of the other. So what does that tell us about the vectors? So one vector is a multiple of the other. We know that that tells us, like in our previous problem, that they are parallel. So AB and DC are parallel, right? And AB is, well, you know what? I'm going to put this I think this should be DC. Forgive me if I'm wrong, but I think this should be DC. So I want to show that AB is whatever times DC. So let me cross that part out. So AB is whatever times DC. Now look at AB. AB is M, DC is 3M. So if DC is 3 times longer than AB, that means AB must be a third of the length of DC. Okay? So AB is a third, let me put that in yellow. Is a third of the length of DC. Now look very carefully at what it says, you know. It never says DC is what times AB. It said AB is what times DC. Okay? So AB. So look at it this way. We know that DC is equal to 3 times AB. So that means AB must be equal to a third of DC, because to get AB by itself, we divide by 3. So if that's the case, that's why we said that it's a third times DC. Everybody seeing that part? So you have to be very careful with what is where, and where we put the vectors is it matters. All right, express BC in terms of M and N. Now this is the fun part. So when we're talking about vectors, again, vectors is just like movement. It just represents movement. You know what vectors is like? You ever go somewhere? Like let's say you live in a scheme. I always like to use this idea. Let's say you live in a scheme. And in your scheme, who here live in a scheme? You know, scheme setup. So you have the roads them proper, and you have the places proper. And let's say you want to go to like the cook shop that is over here. So it's summer, you're hungry. And you're leaving from your house. But you know, say in the scheme, you have other houses there, blah, blah, blah. And if you want to go to the cook shop, yeah, you could try and kind of cut through the people them yard to get to the cook shop. So you could kind of try and walk from here to here. So, but what you can't do that. Probably you meet up, probably people them yard fence up, seen, or probably you try to walk through the yard and a dog bite you. Seen, so this dog him catch you. So that's how dog look, right? Yeah. Yeah. So him catch you, you can't really walk through that way. But what can you do instead? Instead, well, not even instead. This not normally you would go this way and then you would go that way. So because you can't go to it directly, you have to travel, you have to stick to the road that you know. I don't know if any of you know that saying shortcut draw blood. So you have to just go on with the long way. Don't take no shortcut. It's kind of the same thing with vectors. See? With vectors, sometimes we don't know the route. So we want the vector BC, but we don't know what BC is. So you see, because we don't know what BC is, we're going to have to walk around. We have to go around. So that means that we're going to have to go this way. Oh, let me get, which color am I? Yeah, yellow. Let me get blue. We have to go and go this way, right? And then we're going to have to go this way. And then we're going to have to go this way to get to BC because we can't just go straight. That makes sense? So we're sticking to what we know because we know what those vectors are. We know what these vectors are over here, and that can tell us what BC is. So basically, let me come over to here. I'm going to have to write here. So hope you guys can see everything still. Vector BC is going to be equal to BA plus AD plus DC. Okay? Because we have to go around. Listen, Michael, I like the sketch, yeah. Have we? Dog, no look too bad. So first, we need to know what these stuff are. Do I know what BA is? Well, I already know that AB is M. And I know that BA is opposite to AB. So that means BA must be negative M. Okay? Likewise, and let me put in the arrows over here. Next, I want to find AD, but I know that AD is N, so I can replace AD with N. And I want to go from D to C, but I know that DC is 3M, so I can just write that there. So now I have written BC in terms of M and N. All I need to do now is to simplify. So we have negative M plus 3M. That's 3M minus M, which is just 2M. So BC must be 2M plus N. All right. So once we just think about the vector as the movement, we're moving from one place to another, then we can solve problems with vector geometry. But you see where the whole opposite thing came in a while ago? We have to be very careful when looking for the opposite, the equal, opposite, parallel, and equal vectors. All right, let's go to the third one. Let us find vector. It says L is the midpoint of CD. So I'm going to rub this part off. L is the midpoint of CD. So I want to find BL in terms of M and N. No, we want to find BL. Let's first, you know what helps is to connect it. You should draw it on the diagram. Remember, the paper is your paper, I know. It's not nobody paper. So in the exam, draw on your paper as much as you want. So we go, so now, boom, from B to L. And so that is vector BL. No, again, we don't know what the root is. We have a little dog here said the way, a fence. We don't know what it is from B to L. So we're going to have to go around. So who can write in the chat? How could I get from B to L? What vectors could I travel along to get from B to L? What say you? Katharina, of course you can understand. Tell me what you're not so sure on. And let's see if we can help you to understand. So tell me where in it you kind of feel a little lost. In the meanwhile, though, guys, tell me how we could travel from B to L. Which vectors could we travel along? Where could we go? Where could we go? Let me see what you guys are thinking. From B to L, because we want the vector BL. Sorry. Let me write it so you see it good. From B to L. So let me zoom in. So we're going from B to L in green here. Where could we travel? So we could go here. We could go this way from B to C and then C to L. All right. Everybody seeing that? So to get from B to L, we could go from B to C and then C to L. That's one way that we could travel, right? Any other ways that we could travel? Any other ways? Anywhere else we could go? Let me see. Oh, you're saying from B to A and A to, oh, you take it back. I take it back. I was reading that. Yes, single kiddo B to C and then C to L. That right. That's what we did. I'm saying, is there any other way that we could go? Another way, and I saw it in the chat earlier, and I don't know why you guys pull back your retract your message. We could go from B to A, and then A to D, and then D to L. The only thing is you guys didn't put in the D, you put N. Right? So we could go that way. Yeah. So guess what I'm gonna do? You see, because I know BC already, and we can figure out CL. I'm not gonna go through the trouble to go through three of them. I'm just gonna pick two. So to go from B to L, we could do BC plus CL. Okay. So could yeah, we could do BC and then CL. So first, do we know what BC is? Yes, we just figured out BC. BC.
Excuse me. So yes. BC CL would have been positive or negative because we're going in the other direction.
Yes, yeah, we're going to go in the other direction. So we soon get to CL and what CL is going to be. All right. But let me just write on BC now. So BC is going to be 2m plus n. Cool. Then now CL. What is CL? As you're saying, Simone, that's right. CL is going in the opposite direction to a vector that we know, DC. I remember it said that L is the midpoint of CD. So if L is our midpoint, it's halfway through. So whatever DC is, L is going to be a half of that. Okay. So that means since CL is going in the, so now guys, follow me very carefully. Again, this whole idea of opposite come into play. CL is going in the opposite direction to DC. Direction matters. So CL is going like this. So it's going to be negative, right? A half of 3m. So let's break that down. So CL is equal to negative half of whatever DC is, because it is half of DC in the opposite direction. Half of DC going in the opposite direction. See? So since DC is 3m, because we want the vectors in terms of m, then this is going to be minus a half of 3m. That's what that is. This is what this is. See it here, so that's what that is. Okay. That part is very important. Is everybody with me on that one? Is everybody clear on why that is? Type a Y in the chat if you're good, or a thumbs up, and an N if you're not sure why CL is negative half of 3m. I just want to make sure that. All right, good. I've seen some person saying, yeah. All right. So that part's really important. So pay attention to negative opposite vectors and stuff like that. So that now, if we can break this down, we can simplify this some more. So that's going to be 2m plus n minus a half of 3m. A half of 3 is 1.5. So we can say that's basically minus 1.5m. And now we can group like terms 2m minus 1. I don't want to really write it as a decimal, and I prefer writing it as fraction. That's just me still. So 2m plus n minus 1.5m. So 2m minus 1.5. 2 minus 1.5 is a half. So that's just a half m plus n. And that is what the vector BL would be equal to. All right. So those are our values for BC and BL. I remember, you know, if we're going along and there are some parts you're not sure about, as I always say, I'm here to help you. So you need to let me know where you're not so sure with, so that I can help you. You understand? So if you feel like there's a part that you don't really understand, let me know, and then we can fix it. Yeah, do we have a Zoom session? Saw that question in the chat. This session is also on Zoom. You can just check the community tab and you will see the link for the session. That can help. I wouldn't say can't do it in decimals, because a decimal just represents a fraction either way, but it's preferred, like, you know, it's kind of preferred for you to do it, write it as a fraction. Yeah, that's what we usually write it as. All right. So it's an hour, guys. Thanks a lot for joining the session. We're gonna stop here. That's the last question we're gonna do, and this would have been the last weekend session that we would be doing. As no, it's May 1st. As I was saying earlier, we're gonna with the extension of the exam, I think we can include some in the week. I think we can include some in the week sessions. So I know a lot of persons were asking for the circuit theorem workshop, and we're going to have that. We're gonna have that this week. Hopefully we have it this Wednesday at 7. Yeah, that's the time I'm planning for. So circuit theorem this Wednesday at 7. If you still want us to do the matrices workshop, then you just kind of let us know. And then we can see what we can do. And of course, going into the exam, we might do 1 or 2 more sessions. We might even do a multiple choice session or something like that. Let's see how it goes. So again, I wish you guys all the best. All the best on your exam. Don't waste the time you get, use it and make sure that you practice. So don't say, 3 weeks, life good. No, make sure you do some work. Yeah. And once you do that, then you'll be good. Oh, I remember you asking about transformation geometry. Yeah, that session too. So you know what? Instead of the past, instead of just doing a whole past paper, I kind of like to focus on specific topics. So yeah, probably might do transformation geometry. So you can look out for that. But any session going forward is going to be in the week, not necessarily on the weekend. All right, everybody. So enjoy the rest of your evening. Have a great week. Remember, make sure that you practice. And all the best. I'll see you guys around. And if you're not subscribed, make sure that you subscribe.